In this question, we have light of a certain intensity L, certain frequency F, shining on a metal plate. Now, under this condition, right, we have the saturation current as I and the stopping potential as Vs. What will change if, right, number one, we use the same intensity, but we will use double the frequency, okay? Firstly, right, let's look at just the frequency change. How will it affect things? So HF equals to work function plus the KE max, okay, which we'll write as EVS. Let's make, right, EVS the subject, okay? So this will become HF minus work function. When you double the work function, right, when you double the frequency, you will cause the photon energy to be twice as large. You still have to compensate for the same amount of work function. When you have twice the photon energy compensating for the same work function, you will have more than twice the KE max compared to before, okay? Therefore, stopping potential will have to be greater than 2 EVS, greater than 2 VS. If you are unclear, right, you can use this method of looking at things. So for the same matter, right, you see we have two scenarios. Original scenario, we have a certain HF. Let's just call it 5 units. When you double the energy, this becomes 10 units. Still the same matter. So let's say the work function is, let's say 3, okay? So you have to minus 3 in both cases. When you have 5 minus 3, you have 2. But when you have 10 minus 3, right, you will have more than twice 2. Okay? Yeah. So that's how you can see it in a very, very concrete ways. So that takes care of the stopping potential part. What about the maximum current portion? So firstly, right, we know that the current, right, number of electrons per unit time is proportional to number of photons per unit time. Yeah. So you got to ask, when we are delivering the same intensity, so this is the same energy arriving per unit time. In the original case, right, we are delivering, right, this intensity, right, in smaller packets. Okay. Yep. Oh, this is the light in smaller packets. So you will need to have, right, you see each packet, how large is that? It's only HF. You need to have more photons to deliver a certain amount of energy compared to later on, right, when you shine the light, each packet, right, is like larger. Oh, how large is this? It's 2HF. So to deliver the same power, deliver the same energy, there will be less photons arriving, okay? Less photons arriving, right, so this one will be halved. Means, right, there will be less current, less electrons emitted. I shouldn't say that the NE over T, right, will be half as well. It will definitely be lesser than the original one. Why can't I say that it's half, right, is because at different frequency of light, there will be a different yield, okay? That means, right, maybe you use a certain purple light, okay? You have a yield of maybe 10%. You use ultraviolet, maybe you have a yield of 15%. So we can't tell for sure, right, that the current will be halved, but we could tell, right, that it will be less than the original because there are simply, right, much fewer photons arriving per unit time. Okay, so that will be less than I. Answer is B.